Late March, 1945. Kustrin, Brandenburg, Germany. The smoke had barely cleared from the street fighting when Soviet troops spotted an unusual Sherman tank abandoned near the Wartha River crossing. This wasn't the standard M4A1 or M4A2 they'd seen in Lend-Lease shipments. The hull sat lower, the tracks were wider, the suspension looked completely different. Within hours, intelligence officers recognized what they'd found. An M4A3E8, the latest American variant with horizontal volute spring suspension. The Soviets knew the Germans would pay dearly for this prize. By April 2nd, through channels that avoided official paperwork, this particular Sherman serial number USA 52917, built by Fisher Body Division in Grand Blanc, Michigan, began a circuitous journey westward into German hands. The price: information about Soviet force dispositions that German commanders desperately needed as their defensive lines collapsed. The tank would reach Kummersdorf proving grounds outside Berlin, just as the Third Reich entered its final weeks. But even in the face of imminent defeat, German tank engineers could not resist one final examination of American engineering. What they discovered during their abbreviated testing program would haunt post-war German armor designers for decades. The Americans hadn't just improved the Sherman. They had solved fundamental reliability problems that had plagued German armor throughout the entire war. The exchange occurred in a devastated industrial suburb where front lines had shifted 3 times in 2 weeks. Soviet liaison officers met their German counterparts in the shell of a factory building. No written agreements, no official documentation, just a straightforward transaction between enemies who recognized mutual benefit despite the ideological hatred between their nations. The Germans needed intelligence about Soviet force concentrations desperately. Their reconnaissance capabilities had collapsed. Luftwaffe aerial. Reconnaissance was practically non-existent. Ground reconnaissance units were too weak to penetrate Soviet lines. Information about where Soviet forces were massing for their final assault on Berlin was worth almost any price. The Soviets wanted this particular Sherman variant intact for their own evaluation purposes. They had received thousands of earlier Sherman models through Lend-Lease, but this latest version with the improved suspension system had only recently entered production. Capturing one undamaged from the Germans, who had presumably already conducted preliminary examinations, served Soviet interests better than waiting for official channels. The tank changed hands at dawn on April 2nd. German recovery crews drove it 40 kilometers westward, staying on secondary roads to avoid Soviet air patrols. The Ford GAA engine ran smoothly throughout the journey. The transmission shifted without complaint. The final drives maintained consistent power delivery. Every kilometer provided evidence of what German tankers had learned to expect from captured American equipment. It simply worked. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The mathematics of armored warfare had always favored the side whose tanks actually reached the battlefield and remained operational. By 1945, German engineers understood this principle with painful clarity. Their testing reports from captured Allied equipment dating back to 1942 had documented American automotive superiority repeatedly. Panthers broke down with disturbing regularity. Tigers required constant maintenance from specialized mechanics. Even the relatively reliable Panzer Mark IV suffered final drive failures and transmission problems that left them immobilized far too often. The M4A3E8 represented America's response to feedback from thousands of combat operations across 2 years of European fighting. Every component reflected lessons learned through hard experience in terrain ranging from Normandy hedgerows to German industrial cities. The Germans called this Sherman variant the Easy 8 after they captured documentation explaining the American nomenclature. The designation puzzled them initially. Why would Americans emphasize that a tank was easy? German doctrine assumed tanks required skilled crews with extensive training. Panther drivers underwent months of instruction learning proper double-clutching techniques to avoid damaging the transmission. Tiger commanders spent weeks studying the complex systems that made their vehicles formidable but temperamental. German tank doctrine was built around the assumption that highly trained specialists would operate sophisticated equipment. The American philosophy assumed ordinary soldiers would operate complex machinery under stress. This wasn't because Americans had lower standards. It reflected a fundamentally different industrial reality. American automotive manufacturers had spent decades designing vehicles that average citizens could operate and maintain. This civilian experience base directly influenced military vehicle design. If millions of Americans could drive Ford automobiles without specialized training, then tank design should apply those same principles of operational simplicity. The captured tank bore marks of recent combat. Scratches from tree branches scarred the turret. Mud caked every component of the suspension system. Shell impacts on the hull armor hadn't penetrated, but had left distinct dents marking near-miss encounters. Someone had painted Thunder on the turret side in white paint, along with 23 small swastika symbols, presumably representing vehicle kills claimed by this crew. German recovery crews drove the Sherman to a secure Wehrmacht depot, 20 kilometers behind the crumbling front lines. The engine ran smoothly throughout the journey. The transmission shifted without complaint. The final drives maintained consistent power delivery. Every kilometer provided additional evidence of automotive excellence that German tankers had learned to recognize and grudgingly respect. At the depot, technical specialists conducted preliminary inspections while awaiting transport authorization to Kummersdorf. What they found contradicted everything German tank design philosophy had prioritized over 6 years of war. The suspension system caught immediate attention from every engineer who examined the vehicle. Traditional Sherman variants used vertical volute spring suspension with 3 two-wheel bogies per side. The springs oriented vertically, providing adequate but unremarkable ride quality and track life. German intelligence had documented this suspension design extensively through examination of numerous captured Shermans since 1942. They understood its characteristics, its limitations, and its adequate but unspectacular performance. The M4A3E8 featured horizontal volute spring suspension with 2 three-wheel bogies per side. The springs oriented horizontally, enclosed in cylindrical housings that protected them from damage and contamination. The tracks were substantially wider, measuring 23 inches compared to the 16-inch tracks on earlier Sherman variants. This wasn't merely a refinement of existing design. This represented a complete redesign of the suspension geometry, load distribution, and maintenance requirements. Someone at American tank development facilities had identified problems with the original suspension system and systematically engineered solutions that addressed every deficiency. German tank suspensions used torsion bars or leaf springs in complex arrangements requiring precise adjustment and frequent maintenance. Tiger tanks used overlapping road wheel designs that looked impressive and provided excellent weight distribution, but collected mud and froze solid in winter conditions, immobilizing entire battalions during Russian winter operations. Panther tanks employed doubled torsion bar suspension that provided excellent ride quality, but required factory-level expertise to maintain properly. The horizontal volute spring system on this Sherman offered several distinct advantages that German engineers immediately recognized. First, the wider track contact patch distributed weight more evenly, reducing ground pressure from 12.7 pounds per square inch to approximately 10.4 pounds per square inch. This improved mobility in soft terrain substantially, allowing the tank to operate in conditions that would bog down narrower tracked vehicles. Second, the suspension travel was substantially greater than earlier Sherman variants, approximately 9 inches compared to 4 inches on vehicles with vertical volute spring suspension. This allowed the tank to maintain higher speeds over rough ground without damaging components or exhausting crews through constant jarring impacts. Crew fatigue was a serious operational concern that German doctrine had never adequately addressed. American designers apparently considered human endurance as important as mechanical specifications. Third, the springs were easily replaced in field conditions without specialized tools or factory-trained mechanics. Each bogie assembly could be unbolted and replaced as a complete unit. Damaged springs didn't require disassembling adjacent components. The entire suspension system was designed for maintenance by ordinary mechanics using standard wrenches and basic automotive knowledge. German engineers had designed for optimization. American engineers had designed for adaptation to real-world conditions. The difference was visible in every component. German suspensions provided theoretically superior performance when properly maintained by expert technicians with adequate tools and parts. American suspensions provided reliable performance when maintained by ordinary soldiers with whatever tools and parts were available. The preliminary inspection also revealed significant changes to the turret design. Earlier Sherman variants had used cast turrets with relatively thick armor but limited internal space. The M4A3E8 featured what American documentation called the T-23 turret, originally developed for a different tank program but adapted to the Sherman chassis when that program was cancelled. This turret was larger, providing more working space for the crew. It featured a more efficient layout of controls and equipment. Most significantly, it was designed to accommodate the 76mm high-velocity gun that American forces had adopted in response to German heavy armor. This particular tank mounted the 76mm M4A3E8 gun, a substantial improvement over the 75mm guns that had equipped most Shermans during the Normandy invasion. German intelligence had tracked American adoption of the 76mm gun with considerable interest. The weapon still didn't match the penetration capability of German 75mm KOK-42 guns on Panthers or 88mm KOK-36 guns on Tigers, but it was adequate against most German armor at typical combat ranges. More importantly, it demonstrated American willingness to continuously improve equipment based on combat experience rather than defending original specifications. German tank development often proceeded according to plans established by high command, with limited feedback from frontline units. When problems appeared, the tendency was to blame crews or tactical employment rather than acknowledge design deficiencies. American development incorporated systematic feedback from combat units. When the 75mm gun proved inadequate against German heavy tanks, American ordnance departments rapidly developed and fielded the 76mm gun. When crews reported visibility problems, improved periscopes and vision devices were designed and installed. When complaints about suspension performance reached development facilities, engineers redesigned the entire suspension system. This iterative improvement process, enabled by America's vast industrial capacity and efficient feedback mechanisms, meant that American equipment continuously improved, while German equipment often remained frozen in specifications established years earlier. The M4A3E8 represented the culmination of this process, a Sherman incorporating every lesson learned through 2 years of European combat operations. April 9, 1945. Kummersdorf Proving Grounds. The Soviet advance was now less than 60 kilometers from Berlin. Artillery fire rumbled constantly in the distance, a sound that had become so familiar that personnel barely noticed it unless shells landed particularly close. Evacuation orders were expected daily. Nevertheless, German test engineers insisted on conducting at least abbreviated trials with this captured M4A3E8. Hauptmann Friedrich Wilhelm, a powertrain specialist who had evaluated captured American equipment since 1943, supervised the testing program. Wilhelm was 41 years old, too old for frontline service but valuable for his expertise in automotive engineering. Before the war, he had worked for Daimler-Benz designing truck transmissions. The Wehrmacht had assigned him to testing duties because his civilian experience made him uniquely qualified to evaluate enemy vehicle designs. Wilhelm understood they had limited time. Soviet forces were approaching rapidly from the east. American forces were advancing from the west. The Reich was collapsing. Berlin would likely fall within weeks. But engineering discipline demanded proper documentation regardless of circumstances. His entire career had been built on methodical analysis and thorough reporting. He would not abandon professional standards simply because Germany was losing the war. His team had perhaps 72 hours before evacuation became mandatory. They would make those hours count. The initial inspection focused on the powertrain modifications. Earlier, Sherman variants had used various engine options depending on manufacturer and availability. The M4A1 typically mounted right R975 radial engines. The M4A2 used General Motors twin diesel engines. The M4A4 featured Chrysler multibank engines. This lack of standardization had initially puzzled German intelligence officers, who assumed it indicated production chaos or poor planning. Actually, it demonstrated something more troubling. American industrial capacity was so vast that multiple manufacturers could produce the same vehicle using different powertrains without creating unmanageable logistics problems. Germany could barely produce adequate numbers of one tank type using one engine. America could produce adequate numbers using whatever engines were available from whichever manufacturers had capacity. The M4A3 standardized on the Ford GAA-V8 engine, a 500 cubic inch aluminum block liquid-cooled power plant producing 500 horsepower at 2600 revolutions per minute. German intelligence had captured documentation about this engine months earlier through various sources. Technical manuals recovered from destroyed vehicles, documents captured during the Battle of the Bulge, information obtained from American prisoners of war who had mechanical training, but seeing the physical installation provided insights no technical manual could convey. The engine sat lower in the hull than earlier radial configurations, improving center of gravity and reducing vehicle height by several inches. This made the tank a smaller target and improved stability during movement over rough terrain. The cooling system used a more efficient cross-flow radiator design with dual electric fans, providing positive airflow even when the vehicle was stationary. German tank cooling systems typically relied on engine-driven fans that provided minimal cooling at idle and sometimes proved inadequate during sustained operations in hot weather. American designers had apparently considered this problem and engineered a solution using proven automotive technology. The air filtration system incorporated oil bath filters that German engineers recognized as superior to their dry element filters for desert and dusty conditions. Oil bath filters trapped particles in oil rather than paper elements, providing better filtration and longer service intervals. German tankers in North Africa had struggled with air filter maintenance in desert conditions. Apparently, American designers had studied this problem and selected filtration technology appropriate for varied environments. Every detail reflected accumulated operational experience systematically incorporated into production. This was perhaps the most troubling aspect of American tank development from the German perspective. It wasn't that American engineers were more skilled or knowledgeable than German engineers. It was that American industrial organization allowed systematic incorporation of combat feedback into production in ways German industry could not match. The transmission inspection revealed perhaps the most significant advancement. Earlier Sherman variants used a sliding gear transmission requiring skilled double-clutching techniques during operation. Drivers had to carefully match engine speed to transmission speed before engaging gears. Mistakes could grind gears, causing immediate damage or accelerating wear that would eventually cause failure. This made Sherman driving demanding but not impossible for adequately trained crews. German tank transmissions were considerably more difficult, using straight-cut gears that required even more precise technique. But at least German and American tanks shared the common requirement for driver skill and careful operation. The M4A3E8 incorporated a synchromesh transmission design with synchronized gears in second through fifth speeds, identical to civilian automotive practice perfected over decades of American automobile manufacturing. Small synchronizing cones matched gear speeds automatically before engagement, allowing smooth shifting without double clutching or careful throttle management. This seemingly minor change had profound implications that Wilhelm immediately understood from his pre-war automotive engineering experience. It meant that drivers required minimal specialized training. Any soldier who could drive a truck could operate this tank with perhaps 8 to 10 hours of familiarization. The equipment accommodated human limitations rather than demanding perfection from operators. German tank transmissions demanded extensive training and constant vigilance to avoid damaging the straight-cut gears through improper shifting technique. A well-trained German tank driver represented months of instruction at specialized schools. An American Sherman driver represented hours of familiarization with equipment designed to forgive operator errors rather than punish them with mechanical failure. Wilhelm drafted notes documenting these observations. His handwriting was precise despite the stress of imminent evacuation and the constant background rumble of artillery fire. He wrote in technical language, avoiding emotional characterizations or defeatist commentary that might cause problems if his reports were reviewed by security personnel. The Americans have applied civilian automotive engineering to military requirements with results we cannot match given our industrial limitations, he wrote. This is not a criticism of German engineering capability. This is recognition of American industrial maturity developed over decades of mass production that Germany never achieved and now never will achieve given current circumstances. The phrasing was careful. Wilhelm understood that even in April 1945, even with Soviet forces approaching Berlin and the Reich visibly collapsing, careless words could still result in arrest and execution for defeatism. But he also understood that accurate technical reporting required honest assessment. He threaded this needle carefully in every report he wrote. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The automotive testing began on April 10th. Engineers drove the Sherman through obstacle courses designed to stress every mechanical system. These courses had been developed over years of testing German and captured Allied equipment, incorporating obstacles that replicated battlefield conditions. Steep inclines, deep trenches, loose sand pits, rocky terrain, and water crossings. They measured fuel consumption carefully, knowing that logistics had always been Germany's weakness. The Wehrmacht had invaded Russia with thousands of horses providing logistics support because Germany lacked sufficient trucks. German tanks consumed fuel at rates that strained supply systems even when those systems functioned normally. American tanks, with their more efficient engines and better designed fuel systems, consumed less while providing comparable performance. Wilhelm's team monitored engine temperatures across varying loads, using thermocouples attached to critical points on the engine block, cylinder heads, and cooling system. They recorded transmission behavior during rapid acceleration and deceleration cycles, listening for grinding sounds or resistance that would indicate inadequate synchronization or design problems. They examined track tension after each trial, looking for evidence of stretching or uneven wear. The results aligned with what earlier testing of captured Shermans had demonstrated, but with measurable improvements in every category. The horizontal volute spring suspension absorbed impacts that would have jarred crews severely in earlier Sherman variants. During high-speed runs over rough terrain, German test drivers reported that the ride quality was noticeably superior to earlier Shermans and comparable to or better than German tank designs. This was significant because crew fatigue was a serious operational concern that German doctrine had never adequately addressed. Tank crews operating over rough terrain for extended periods suffered exhaustion that degraded combat effectiveness. German commanders typically attributed this to insufficient crew conditioning rather than mechanical design problems. American designers apparently understood that reducing vibration and impact transmission improved crew endurance and therefore operational capability. The improved weight distribution reduced track wear noticeably compared to vehicles with vertical volute spring suspension. Earlier, Shermans averaged approximately 1,600 kilometers before track replacement became necessary. Based on wear patterns observed during testing, Wilhelm estimated that the M4A3E8 tracks would last at least 2,000 kilometers under similar conditions, possibly longer. This represented substantial logistics savings multiplied across thousands of vehicles. Fewer track replacements meant less manufacturing capacity devoted to producing replacement tracks, less shipping capacity transporting tracks to forward areas, less mechanic time installing replacements, and fewer vehicles temporarily out of service for maintenance. These incremental advantages accumulated into significant operational benefits. The synchromesh transmission eliminated the grinding sounds and mechanical resistance that characterized German tank transmissions under hard shifting. Test drivers, all experienced German tankers with thousands of hours operating Panthers and other German armor, reported that the Sherman transmission was remarkably easy to use. One driver commented that it felt more like driving a civilian truck than operating a military tank. This comment captured precisely what American designers had achieved: military equipment with automotive refinement that made it accessible to ordinary soldiers rather than demanding specialist expertise. German tank development had pursued performance specifications while accepting operational difficulty as an inevitable cost. American development pursued adequate performance while prioritizing operational accessibility. Most significantly, the final drives showed no signs of stress even after sustained high-load operations. Final drive failure had plagued German tanks throughout the war. Panthers suffered catastrophic final drive breakdowns with disturbing frequency, particularly in early production models. Tigers required final drive replacements after relatively modest operational mileage, sometimes as little as 1,500 kilometers under hard service. The Sherman's final drives simply worked, hour after hour, without the precise maintenance intervals that German designs demanded. Wilhelm could see in the design that American engineers had built substantial safety margins into the final drive assemblies. They were larger and heavier than German designs, sacrificing some theoretical efficiency for enormous practical robustness. German engineering culture emphasized optimization, extracting maximum performance from minimum weight and size. This produced impressive specifications but left little margin for error, abuse, or deviation from ideal operating conditions. American engineering culture emphasized adequate performance with substantial design margins to tolerate real-world conditions, including operator error, inadequate maintenance, poor fuel quality, and combat damage. On April 11th, with Soviet artillery now audible even during daylight hours and clearly closer than the previous day, Wilhelm conducted hill-climbing trials comparing the M4A3E8 against a Panther OSF-G, one of the last operational vehicles remaining at the facility. Most equipment had already been evacuated or destroyed to prevent capture. This Panther represented one of the few German tanks still functional. The comparison was arguably unfair to both vehicles for different reasons. The Panther represented Germany's most sophisticated medium tank design, incorporating every lesson German engineers had learned through 4 years of war. It featured superior armor protection, a more powerful gun, and impressive automotive performance when properly maintained. But this particular Panther had seen hard service. Its maintenance history was incomplete. It probably needed final drive replacement and certainly required transmission service that hadn't been possible given collapsing logistics. The Sherman represented American incremental improvement of a design already in production when Germany invaded Russia. It lacked the Panther's firepower and armor protection, but it was fresh from combat service with adequate maintenance. Its mechanical condition was good. Every system functioned as designed. The Panther climbed the test slope with its characteristic power, the 700 horsepower Maybach HL 230 engine, providing impressive performance despite the vehicle's heavy weight. But the transmission required careful management from the experienced test driver. He double-clutched precisely, managing throttle input to avoid shocking the drivetrain with sudden torque changes. One mistake could damage components that would require factory-level repairs that were now impossible given Germany's situation. The driver was Oberfeldwebel Hans Zimmermann, who had trained dozens of Panther crews and knew the vehicle's temperament intimately. He understood exactly how to coax maximum performance while avoiding the mechanical stress that would cause failures. His skill was evident in every gear change, every throttle adjustment, every careful manipulation of controls. This illustrated the fundamental difference between German and American design philosophy. The Panther required an expert driver to achieve its potential. The Sherman was designed so that adequate drivers could achieve acceptable performance. Germany assumed expertise would be available. America assumed it wouldn't, and designed accordingly. The Sherman followed up the same test slope. The driver was Unteroffizier Kurt Schmidt, a German tanker with extensive experience on Panzer Mark IVs, but only 30 minutes of familiarization time on this captured Sherman. He handled the vehicle confidently despite minimal training. The synchromesh transmission shifted smoothly without requiring precise technique. The Ford GAA engine maintained steady power delivery across the rev range without the careful throttle management that German engines demanded. The horizontal volute spring suspension absorbed terrain irregularities without bouncing the hull or unsettling the driver. The tank climbed steadily without the mechanical drama that accompanied German tank operations. Schmidt reported afterward that he felt comfortable operating the vehicle despite his limited experience with American equipment. Wilhelm watched both ascents carefully, taking notes on a clipboard while standing in the cold April wind. He understood what he was witnessing. German tanks were faster, better armed, and better armored when everything functioned properly and expert crews operated them under favorable conditions. But when everything functioned properly was a condition German tanks achieved inconsistently, particularly as crew quality declined and maintenance capacity collapsed. The Americans had built a tank that functioned properly as its default condition. Maintenance didn't prevent problems. Maintenance was simply routine service that ordinary mechanics could accomplish with standard tools. Adequate drivers could operate it effectively without months of specialized training. The equipment accommodated human limitations rather than demanding perfection. That afternoon, Soviet artillery struck the proving ground's outskirts for the first time. Shells landed approximately 1 kilometer from the main testing area, close enough that everyone could hear the distinctive crump of impacts and see smoke rising from the strike zone. Evacuation orders arrived shortly afterward from Wehrmacht command. All personnel were to withdraw westward beginning immediately. All equipment that couldn't be evacuated was to be destroyed to prevent capture. The testing program ended after less than 60 hours, instead of the typical weeks-long evaluation that captured equipment normally received. Wilhelm compiled his notes into a brief technical report, knowing it would likely never reach appropriate authorities through normal channels. The Reich was collapsing. Command structures were disintegrating. Communication networks were failing. His report would probably be filed and forgotten, if not simply destroyed during evacuation or lost in the chaos of retreat. He wrote the conclusion anyway, a final professional assessment from an engineer who had spent years evaluating enemy equipment and who understood what he had witnessed. The M4A3E8 represents the maturation of American tank design philosophy. They have not pursued theoretical perfection. They have pursued practical functionality refined through systematic application of combat experience. The result is a vehicle that ordinary soldiers can operate effectively, that field mechanics can maintain without specialized training, and that logistics systems can support under adverse conditions. He continued, Germany never achieved this despite superior technical knowledge because we lacked the industrial infrastructure and civilian automotive experience America developed over decades. This gap decided the armored warfare competition before the first shot was fired. Our tanks are faster and more powerfully armed when they function properly. Their tanks function properly consistently. In sustained operations, consistency defeats superiority. Wilhelm sealed his report in a folder with other documentation from the abbreviated testing program. He packed his personal belongings, technical manuals, notebooks filled with observations from years of evaluating captured equipment, photographs of his family that he kept in his desk drawer. The evacuation would begin at dawn on April 12th. Soviet forces would likely reach Kummersdorf within 48 hours. The captured M4A3E8 was abandoned at Kummersdorf when Soviet forces overran the facility on April 21, 1945. German personnel lacked time and transportation capacity to evacuate equipment. Demolition was considered but ultimately not implemented, because Wehrmacht sappers were needed elsewhere for more critical tasks. The Sherman sat beside a Panther and a Tiger II, all three vehicles intact and operational, waiting for their new owners. Soviet recovery crews found the tanks on April 22 during their systematic search of the facility. The contrast was stark and immediately obvious to Soviet engineers who accompanied the combat forces. German tanks required extensive maintenance logs, specialized tools, and factory-trained mechanics to keep operational. The Sherman required basic automotive knowledge and standard wrenches. Soviet engineers conducted their own brief evaluation before the tank disappeared into their captured equipment program. Their observations mirrored what German engineers had documented: exceptional reliability, straightforward maintenance requirements, and design philosophy that prioritized operational availability over technical specifications. The Soviets, who had received thousands of M4A2 Shermans through Lend-Lease, recognized the M4A3E8 as a substantial improvement on an already reliable platform. Soviet tank designers were particularly interested in the horizontal volute spring suspension system. Soviet tank design traditionally emphasized low profile, heavy armor, and powerful guns, while accepting uncomfortable crew conditions and difficult maintenance as acceptable. Trade-offs. The Sherman demonstrated that these trade-offs weren't inevitable, that tanks could be reliable and maintainable without sacrificing combat effectiveness. This influenced post-war Soviet tank development in subtle ways. While Soviet designs continued emphasizing different priorities than American tanks, post-war models incorporated more attention to reliability and maintainability than wartime designs had featured. The lesson that operational availability mattered as much as combat capability was learned by both German and Soviet engineers through examining American equipment. The story of this particular tank ends there, lost in the chaos of post-war equipment disposition. Soviet records from this period are incomplete. The tank was probably eventually scrapped, though it might have been used for extended testing or training purposes. Its ultimate fate is unknown, but the lessons it taught continued influencing armor design for decades. To understand why the M4A3E8 represented such a significant achievement, it's necessary to examine the broader context of American versus German tank development philosophy. These differences weren't simply matters of engineering approach. They reflected fundamentally different industrial realities and military requirements. Germany entered World War II with limited industrial capacity concentrated in specific regions vulnerable to bombing. German automotive industry before the war was small compared to America's vast automobile manufacturing sector. Germany produced approximately 300,000 civilian automobiles annually in the late 1930s. America produced approximately 4 million annually during the same period. This 13-to-1 production ratio reflected not just factory capacity, but accumulated expertise, trained workforce, supplier networks, and manufacturing technology. American automotive companies had decades of experience mass-producing vehicles for civilian markets where reliability, maintainability, and cost-effectiveness determined success. German manufacturers had limited experience with true mass production, focusing instead on smaller quantities of higher-quality vehicles for wealthier customers. When war began, both nations applied their existing industrial capabilities to military production. Germany built tanks the way they built limited production automobiles, emphasizing quality, performance, and sophisticated engineering. America built tanks the way they built mass-market automobiles, emphasizing reliability, maintainability, and production efficiency. The results reflected these different approaches. German tanks featured impressive specifications: powerful guns, heavy armor, sophisticated fire control systems, and advanced automotive technology, including torsion bar suspension and interleaved road wheels. But they required extensive maintenance, specialized training, and constant expert attention. Production numbers were limited by manufacturing complexity and industrial capacity constraints. American tanks featured adequate specifications: guns sufficient for most combat situations, armor adequate against most threats, and straightforward systems that ordinary soldiers could operate and maintain. Production numbers were enormous because American industry had mastered mass production techniques and applied them ruthlessly to military requirements. By 1945, the outcome was clear. America produced approximately 49,000 Sherman tanks of all variants during the war. Germany produced approximately 25,000 tanks of all types combined, including light tanks, medium tanks, and heavy tanks. This 2-to-1 American advantage in production, combined with superior reliability that kept more American tanks operational, created overwhelming numerical superiority that German tactical skill and technical sophistication could not overcome. The reliability advantage was substantial and well documented. American armored units typically maintained operational readiness rates above 75%, sometimes exceeding 90% when supply lines functioned normally. This meant that a tank battalion authorized 80 tanks would typically have 60 to 70 tanks operational and available for combat missions. German armored units frequently reported operational readiness rates of 50% or lower, not primarily because of combat losses, but because of mechanical failures and inadequate maintenance capacity. A panzer battalion authorized 80 tanks might have only 30 to 40 tanks operational at any given time. The rest sat disabled, awaiting parts, repairs, or maintenance that couldn't be completed given available resources and personnel. This meant American commanders could rely on their tank units being available when needed for offensive operations, defensive missions, or exploitation opportunities. German commanders had to plan around expected mechanical failures and limited operational availability. They couldn't assume their authorized strength would be available. They had to account for the reality that many tanks would be non-operational for mechanical reasons. The mathematics of this reliability gap were brutally straightforward. If German tanks had 2-to-1 performance advantages in firepower and armor protection, which was generous given actual combat results, but American tanks had 2-to-1 availability advantages, the benefits essentially cancelled out. A German tank that couldn't reach the battlefield because of mechanical failure had zero combat value regardless of its impressive specifications. But American tanks also had overwhelming numerical superiority. When reliability advantages combined with numerical superiority, the outcome was predetermined. German tank crews might win individual engagements through superior firepower, better armor protection, or tactical skill, but they couldn't win sustained campaigns when they were outnumbered 3-to-1 by enemy tanks that were operational 3 days out of 4, while their own tanks were operational 2 days out of 4. German engineers at Kummersdorf understood this by April 1945. They had tested captured American equipment since 1942. They had documented American advantages repeatedly in detailed technical reports. They had written careful analyses explaining why American tanks, though inferior in many specifications, were superior in the only metric that truly mattered, operational availability, that enabled sustained combat operations. But understanding a problem and solving it are fundamentally different challenges requiring different capabilities. Germany lacked the industrial infrastructure to retool production around reliability principles, while fighting a losing war on multiple fronts against enemies with superior resources. The civilian automotive industry that gave America its decisive advantage in designing reliable, maintainable military vehicles simply didn't exist in Germany at comparable scale or sophistication. The post-war period demonstrated how thoroughly German engineers had learned these lessons, even if they learned them too late to affect the war's outcome. When West Germany began developing the Leopard 1 main battle tank in the 1950s and early 1960s, designers consciously emphasized reliability and maintainability over pure performance specifications. They studied American automotive engineering principles extensively and deliberately incorporated them into military vehicle development. The Leopard 1 featured robust powertrains with substantial design margins that tolerated abuse and difficult conditions. It required straightforward maintenance using minimal specialized tools. It used standardized components that enabled rapid field repairs. It incorporated growth potential, allowing future upgrades without complete redesign. The tank's success vindicated this approach completely. The Leopard 1 became one of the most successful tank designs of the Cold War era, serving with numerous armies worldwide and remaining in production for decades. Modern German tanks, including the Leopard 2 currently serving as NATO's primary main battle tank, continue reflecting these priorities. German tank designers no longer pursue specifications without regard to reliability and maintainability. They understand, through hard lessons learned examining captured American equipment during World War II, that operational availability determines effectiveness more than any individual technical specification. The M4A3E8 Sherman that German engineers tested briefly at Kummersdorf in April 1945 represented the full maturation of American tank design philosophy applied across 4 years of war. It wasn't the most powerful tank in service. It wasn't the best protected tank available. It wasn't the fastest tank or the most sophisticated tank technologically, but it was reliable, maintainable, and available when needed for combat operations. These qualities, combined with overwhelming numerical superiority and adequate performance in firepower and protection, made it a war-winning weapon system. German engineers recognized this even as their nation collapsed around them and Soviet shells fell on Berlin. Their technical reports documented American advantages with professional precision and scientific rigor. Their conclusions acknowledged that Germany had lost the industrial war long before the final military defeat became inevitable. The story of captured Shermans, from the M4A1 tested extensively in 1943 through the M4A3E8, examined hastily in the final weeks of the war, reveals a truth about industrialized warfare that transcended World War II and remains relevant today. Material abundance systematically applied through competent engineering and adequate tactical execution will defeat technical excellence, constrained by resource scarcity and industrial limitations. The nation that builds weapons that work reliably and can be produced in overwhelming quantities, while simultaneously producing everything else a modern military requires, will inevitably defeat opponents who build technically superior weapons in insufficient quantities. Germany learned this lesson through bitter experience. The captured Shermans sitting in German testing facilities wearing hastily painted Balkenkreuz markings over American stars were tangible proof of American industrial superiority that no amount of German tactical skill or engineering sophistication could overcome. The M4A3E8 represented not just an improved tank, but a complete manifestation of American industrial philosophy applied to military requirements. Design adequate equipment that ordinary soldiers can operate without extensive specialized training. Build it in overwhelming quantities using mass production techniques perfected in civilian industry over decades. Make it reliable enough that field mechanics can maintain it using standard tools and basic automotive knowledge. Supply it through logistics systems that can deliver parts and fuel anywhere armies operate across global distances. Continuously improve based on systematic combat feedback rather than pursuing theoretical perfection according to specifications set by high command. This approach, perfectly exemplified by the EZ-8 Sherman, proved decisively superior to German methods across every metric that mattered for sustained military operations. Technical sophistication without industrial depth meant nothing when factories couldn't produce adequate quantities. Impressive specifications without reliability meant nothing when tanks sat disabled awaiting repairs. Individual vehicle superiority without numerical advantage and operational availability meant nothing when enemy forces could replace losses faster than they accumulated. The Germans understood this by 1945 through their systematic testing of captured equipment. They had examined the evidence carefully. They had documented the results professionally. They had reached correct conclusions about American advantages and German limitations, but the knowledge came too late to matter strategically. By the time Wilhelm wrote his final report at Kummersdorf in April 1945, the war's outcome had been decided by industrial mathematics that no amount of German engineering skill or tactical brilliance could overcome. The captured M4A3E8, tested hastily as Soviet forces approached and then abandoned to its fate, represented a future that had already arrived. A future where industrial capacity determined military outcomes more decisively than individual weapon superiority. A future where reliability and maintainability mattered more than impressive specifications. A future where America's vast industrial base and automotive expertise provided advantages that smaller nations could not match, regardless of their technical knowledge or tactical skill. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.